Welcome back to the C programming language in action. In this module, we're going to learn all about working with strings. In most of today's contemporary languages, including C++, strings are objects that can be manipulated almost as easily as numbers. But there's a great deal of abstraction that makes that level of convenience possible. Usually that's fine, but sometimes the cost is simply too great, particularly in embedded systems programming. Even for many applications where string searching and sorting is critical, having a good understanding of the fundamental string management functions provided by C can be very beneficial. Strings are made up of characters, and by convention they are null terminated. We've already seen this in action, but in this segment I want to look a little more closely at individual characters. Consider a simple string. This is a null terminated string. The null terminator or zero character is hidden, but it's there. We've already seen how this works in previous modules. We also routinely added a new line character to the end of many strings. That's the new line escape sequence. Those two characters in the source file are considered a special escape sequence that the compiler interprets as a single character, the new line character. Often that's enough to move the cursor, so to speak, or the output in the file stream to a new line so that you can write the next line of characters. Some mediums may require something more like a pair of characters. First a carriage return, followed by a new line. You can think of a typewriter, and your mental model would not be far off. We can now include a few characters to be presented on the next line. Let's check it out. As you'd expect, Hello World is followed by Goodbye. But this looks the same as if we'd simply used the new line character. And indeed it is. It really depends on the environment in which the text will be presented. But be careful you don't opt simply for the carriage return. Now the console interpreted the carriage return to mean you want to move or return to the start of the line, but not to the next line. So the second line of text was printed over the first. That might sometimes be what you want, but probably not. Certainly would not work with output streams for which you do not have random access. Many I/O streams only let you write in a forward-only manner. But the carriage return is not useless. The HTTP protocol, for example, requires that request and response lines, the individual headers, are terminated with a pair consisting of a carriage return and a new line, even though they are never displayed in the browser. It's just part of the protocol. There are, of course, other escape sequences. You might have come across the tab. But this brings up the question of escaping the escape characters. These are known escape sequences, but what if you want to include them quite literally? What if you want a backslash to be printed or a double quote? No problem. Just double up on the backslash or escape the double quotes. Here I've quoted the message. Printing something like a DOS-style path also requires that I double up and use two backslashes everywhere one might appear. But forward slashes are unaffected. Let's take a look. Sure enough, the Hello World message is quoted naturally. The path looks right with single slashes, and the web address is printed plainly. When we look at character strings such as this, it's often useful to be able to classify the characters such that we know, hey, is this a digit, an alphabetic character, punctuation, whitespace, uppercase, lowercase, and so on. Fortunately, we don't have to provide this intelligence. The C standard library provides a set of functions for classifying characters. Let's loop through the characters in the string. And I'll just copy each character to a local for convenience. And then we can begin to print them out. So that's the character followed by a tab character. Of course, as you'll soon see, this is not always going to give us the desired effect. After all, we may end up printing out control characters. But I'll show you how you can detect those as well. Now we have a dozen or so functions for classifying a character. We need to include the appropriate header in order to use them. First, it's often useful to know whether a character is alphanumeric. This will be true if the character is a digit, a lowercase letter, or an uppercase letter. But sometimes you might want to exclude the digits. Or limit it further to only lowercase letters. Or uppercase letters. Perhaps you're only interested in digits. You may want to broaden the definition slightly and accept alphanumeric digits that are used by hexadecimal numbers only. What about control characters, tabs, new lines, and so on? Or simply characters that have a graphical representation. That includes digits, upper and lowercase letters, and punctuation characters. You might want to interpret white space characters, perhaps to develop a parser or search for words. Or you might want to limit it to space within sentences, horizontal blank space. Perhaps you just want to know whether it is a printing character. A printable character is distinct from graphical characters in that it includes white space, since that still affects printing output for layout. And finally, we can isolate punctuation characters. Okay, let's throw in a new line and see what happens. Great. So on the left, we can see the characters in a column. Next to each, we see the various classifications. It should now be obvious, if it wasn't before, that particular characters may qualify in any number of categories. The H in hello, we can see that it's an alphanumeric character. An alphabetic character, it's an uppercase letter, has a graphical representation, and is a printing character. The following E, however, while it's also an alphanumeric character and an alphabetic character, it's different in that it's a lowercase letter and also qualifies as hexadecimal character. As we go down the list, we can also see the gaps. Those, of course, were caused by printing out the control characters, the new line characters in this case. Okay, so you have a good idea of character classes and how to identify them quite easily. Let's move on. In this segment, we're going to consider character manipulation. We already looked at how to convert numbers to strings with the sprintf function. But what about the other way around? In this segment, we'll begin with the simple matter of converting between upper and lowercase letters. In the next, we'll specifically look at numbers. We can walk the string, use the character classification functions we just learned about, and flip the case of each alphabetic character. So there's a loop variable simply iterating over each character until it reaches the null terminator. Now, if we come across an uppercase letter, we can simply replace it with a lowercase counterpart. On the other hand, if we come across a lowercase letter, we can replace it with the uppercase equivalent. Notice that we're only affecting characters that already qualify as upper and lower case, so we'll skip right over control characters, digits, punctuation, and so on. Let's print out the tweaked message and check it out. Excellent. So we can convert between upper and lowercase letters. How about strings to numbers? That's up next. We're going to consider number conversion. The C standard library provides functions for that as well. They're not ideal, but they do the trick, provided you already know your input is somewhat reasonable. If you need fine control, I suggest you adopt regular expressions or write your own parser. Still, if you need to quickly convert strings to numbers and you're reasonably comfortable that your input is sanitized, then it's quite straightforward. We can convert a floating point value with A to F. You can think of the A standing for ASCII or ANSI, and there are some non-standard extensions to cover Unicode. So you could write the W to F as well with some compilers, W meaning wide character. There's also a corresponding A to I for integers. And you'll discover variants for long integers as well. But let's print these out and have a look. We just need to include the standard lib header for these conversion functions. Let's give it a try. Pretty much as you'd expect. We can also use stringified versions of these that provide a bit more control and tell us how much of the source string the parser consumed. Let's say we have a string with 3 very different numbers. The first is a decimal number, the second is a hexadecimal number, and the last a binary number. We need a pointer to keep track of our progress. And then we can call the string to long function. The second parameter is a pointer to a pointer that will be updated by this function to point to the character past the last character that was interpreted. All of these functions will simply skip whitespace, so we're good. The final parameter tells the function that we'd like to interpret the number as a base 10 number, a decimal number. Now the second number. Now, notice that we're using the updated next pointer as input and getting the function to update it on completion. We're also using the curious 0 as the base number system. 0 tells the function that it should try to figure out the number system based on the input. It should detect the OX prefix customary for hexadecimal numbers and interpret it as base 16. But if the prefix were missing, the function would just assume a decimal number and we'd have to be explicit and indicate this as base 16 as the final parameter. And now the final number. Here again I'm being explicit and indicating base 2 for binary. Okay, let's see if this successfully interprets the values. And sure enough, 123 in hexadecimal is 291, and 101 in binary is 5. In a more general sense, working with strings involves examining strings, finding their length, comparing them, searching them, and manipulating them in various ways, shortening, concatenating, and so on. That's the topic of this segment. This is where languages like C++ really shine by providing first-class overloaded operators that make it seem so simple. But all those abstractions come at a cost, usually negligible, but sometimes prohibitive. Let's see how we can perform some basic string manipulation directly in C. First, some basics. We don't always have a literal array which we can query at compile time for its length. Often we simply have a pointer to a null-terminated string. How long is this then? That's the job of the strlen function. Strlen, or string length, as with most of the string management functions, comes courtesy of the string header. Next to finding its length, comparing two strings is about the most common thing you might do. For that, we have the string compare function, and about the most common mistake is to assume it only compares for equality, and a non-zero value means it's equal. That's roughly the opposite of how it actually works. Let me illustrate. Here I'm comparing the message "Hello World" with apples. The string on the left sorts higher than the value on the right, so a value of 1 is returned. We say that the value on the left is greater than the value on the right. Here I'm comparing the message "Hello World" with oranges. Now the string on the left sorts lower than the value on the right. We say that the value on the left is less than the value on the right, so a value of -1 is returned. Finally, we compare equivalent string values. Now the value on the left is equal to the value on the right, so a value of 0 is returned. Notice how there are three possible values, -1, 0, and 1. This allows this function, and indeed it's used quite often, to be able to sort strings. Had it only returned equality or inequality, it would not have been nearly as useful. Let's check it out. And first we see that the string length function reports the length or size to be 11 characters. Not including the null terminator. And we can see that the three values reported by the string compare function, 1, -1, and 0. There are also functions for comparing substrings, finding characters, counting spans, and much more. In this module, we've covered the essential principles for working with strings. We looked at escape sequences and how they can be used to control output and escape literal characters. We looked at character classifications, how you can distinguish between alphabetic characters, digits, punctuation, control characters, whitespace, and more. We considered a few techniques for numeric conversion. and how to examine and compare strings. Remember, you can also use sprintf to format strings, to combine different strings together with a great deal of control. Although the standard library provides discrete functions for concatenating strings, it's very easy to get them wrong. sprintf and the secure variants provided by the Visual C++ libraries provide a more robust alternative in many cases.